Good morning, guys. Today we're going to start talking about polynomials. So I just want to go over a little bit of terminology first. Before we talk about polynomials, we have to talk about monomials. A monomial is the product of a number and a variable, and that variable has to have a whole number exponent. So it's like saying 3x to the second power, 3x squared. There's a number, there's a variable, the variable has an exponent. That variable can have any exponent as long as it's a whole number. So anything from 0 to positive infinity is considered a whole number as long as it's 1, 2, 3, 4, 5, all your counting numbers and 0. I guess technically we couldn't have infinity because we can't count infinity, but you get the idea. 0, 1, 2, 3, 4. I can't have any negative values. I can't have any square root or e or pi values, which are irrational. I can't have any fractional values. Has to be counting numbers and 0. If it has one of those other types of exponents, then it's not a polynomial, it's a different type of function. It's not a monomial, it's a different type of function. So, monomial, a number, and that number can be 1, that number can be 0, that number can be any real number. So, any real number, and then the variable has to have an exponent of 0. Okay, 0 or the counting numbers. Now, a polynomial, poly just means many, so many nomials. A monomial, mono means one nomial. So, one term, many terms. So it's the sum of monomials. So it's where I take a bunch of products of numbers and variables and add them all together. And we've been working with some of these before. Our quadratics, our polynomials, ax squared plus bx plus c, our linear functions, mx plus b, or if you want to do it, mx plus b, those would all be polynomials. Standard form is the same standard form like I just talked about, where the terms of polynomial are written in order by decreasing degree, such as with the quadratic function. Standard form is ax squared plus bx plus c. Do the second degree term first, first degree term second, and then the constant goes down at the end. So you've done this before. It's just kind of putting names and specific definitions to why we call that standard form. We use that same standard form always. The degree, you should know, is the exponent on the variable, and then the degree of the polynomial is the largest exponent on a variable for the entire polynomial. So when we talk about degree of a term, we're looking at the exponent in that term. If we're talking about degree of the polynomial, we look for the largest exponent that's on a variable. If I had like a 5 squared in the problem, or a 5 cubed, or 5 to the 10th power, that's not the degree because we can evaluate 5 to the 10th power. The degree is what we can't evaluate. It's the exponents that are on variables. So degree of the polynomial is the largest exponent on a variable in the entire function or entire expression. Okay, couple of ways that we can talk about naming polynomials, and give me a second and I'll get those terms up here on the board. Here we have the classifications for polynomials. It's just kind of a way to name a polynomial. There's two ways we can name them, by degree and by number of terms. So some of this terminology should look very familiar to you. X to the 0 power, if we're talking about classifying by degree. To the 0 power means we have no x's in the problem, so it's a constant. It doesn't vary if there are no variables. And again, doesn't always have to be x. We're just going to work off of x's because of how we're going to get into graphing. But it could be any variable as long as you're consistent and use that same variable each time in the polynomial. So if I have my variable to the 0 power, we'll call that a constant because there is no variable, so it does not vary. To the first degree we know is linear. To the second degree is quadratic. Those we're familiar with. X to the third is x cubed, so that's a cubic. X to the fourth is a quartic, like 4 quarters make a dollar, or 1/4 is a quarter. To the fifth is a quintic, and x to the sixth is a sixth degree. So we'll have special names up to about degree 5. Then we just say whatever the degree is, it's that number to that degree, or it's to that degree right there. So x to the sixth degree. So x to the n is the nth degree. It could be a 10th degree. It could be a 50th degree. It could be a million, x to the million, and it'd be millionth degree. So special names for the degrees up to about 5, and then from then on we just kind of just say what the degree is. If we're classifying by terms, that's how many different monomials are we adding together. If there's only one term, it's a monomial. Remember we talked about that, mono meaning one. 2 terms is a binomial, bi meaning 2. 3 terms is a trinomial, tri means 3. So you're familiar with those because we've been using them. 4 terms, we don't have a special name for, so we would just call it a polynomial of 4 terms. So we're pretty good up to about 3 terms. We've got special names for those, but from then on, we just say it's a polynomial of that many terms. So n terms is polynomial of n terms. Just some terminology, be familiar because we will use these special words a lot just as you progress up into your throughout your math courses and a lot this year. We'll make sure that we get really good at talking math and not just doing math. So here's how we classify polynomials based on their degree or their number of terms. I'm going to put up some examples and we'll look at just how we can do some arithmetic with polynomials as far as adding, subtracting, and multiplying polynomials. So I have a few examples here of what it looks like, how you're going to be presented with exercises for just simplifying some polynomials. We'll talk addition and subtraction right now, and then I'll put up some multiplication problems for you. So really, you know how to simplify these type of expressions. It's just going through and combining like terms. Combine the coefficients using the whatever indicated operation is for terms that have the same exponent on their variables. So if I look at the first example, 2x squared plus 3x minus 4x cubed minus x squared plus 3x minus 5. Combining like terms. So 2x squared minus, it can only combine with the other x squared, so negative x squared. So 2x squared minus negative x squared gives us whatever it gives us. So we put our 2x squared and our negative x squared together. Next, we're going to put the x together, the 3x, the linear term. Well, I've got 3x minus 3x. So we've put them together. Well, we don't have any like terms to combine those two with, so we just add them on. And that's a negative 4x cubed. That's going to be a negative 5. Okay, so we've got to make sure that this negative gets applied to everything. This minus is applied to everything in that second set of parentheses. So now we've accounted for every term in the expression. Then you just put your like stuff together. 2x squared minus the negative is plus x squared. So 3x squared. 3x minus 3x cancels, gives me no x's. I've got negative 4x cubed. I've got negative 5, which is positive 5. But we're not finished yet because we want to put it in standard form. So standard form says largest exponent first, or largest degree term first. So negative 4x cubed, and then we just work our way down the line as far as degree is concerned. So next will be the 3x squared. If I had an x, it would come next, but they was canceled, so I'm left with my constant there on the end. And that wants me to classify my answer. So we've combined our like terms, we classify our answers together, and we see that we do it by degree and then number of terms. So the degree is third degree, that's a cubic. And then the number of terms, 1, 2, 3 terms, and that was a trinomial. Cubic, trinomial. All right, we have 2 more examples up here. I want you to pause the video, take a couple of moments, and simplify this expression, then classify those by degree and number of terms, and I will wait right here, guys. So hopefully you were able to solve or simplify each of these expressions. Let's go through and check your work. So here we have the sum of these two. We're going to put our like terms together. So 5x to the 10th and 3x to the 10th plus 8 is a constant plus negative 7. So 8 plus negative 7. 5x to the 10th plus 3x to the 10th. So we put our like terms together. We've used everything. Gives us 8x to the 10th. 8 plus negative 7 is 1. And then let's classify it now. We're already in standard form. If we classify this, the degree is 10. So we know that that's 10th degree. And then we have two terms. 8x to the 10th plus 1 is two terms. So that's a binomial. So 10th degree binomial, 8x to the 10th plus 1. Well, let's look at this second one here. Putting all of our like terms together. So 2x squared minus 2x squared plus, because remember a polynomial is the sum of terms. So even if we're subtracting here, it's that difference plus the next difference plus the next difference. So it's going to be a sum of all these differences. So 2x squared plus 2x minus 2x squared plus 3x minus 3x plus negative 1 minus negative 1. Actually combine them. 2x squared minus 2x squared cancels. 3x minus 3x cancels. Negative 1 minus the negative, that's plus. So negative 1 plus 1 cancels. So we're left with nothing. Well, polynomial's got to have something. We can't just say it all canceled. Well, it all cancels to give us 0. So we want to, that's the simplified expression. It's in standard form. Now we need to classify it by degree and number of terms. So the degree is, we'll see the degree. What is the exponent on this variable? Well, it doesn't have a variable, so it has no x's in it, right? So it's 0 times x to the 0. So that's going to be a constant. Remember, no x's, no variables is a constant. So the degree tells us it's a constant. And how many terms are there? Number of terms, just one term right there, 0 sitting all by itself, is a monomial. So we have a constant monomial, and that would be 0. But constant monomial is not an expression that we use. We say monomial for something with a variable in it. And the reason we don't put monomial with constant is because if we're writing in standard form, we do our largest degree first. Well, if our largest degree is an exponent of 0, then obviously it has to be a monomial. There can be no other terms after, because 0 is our smallest whole number. So we won't write constant monomial. If we have a constant, we just call it a constant. No variables, simplified, or once we've simplified and combined all our like terms together. Give me a second and I'll get a couple of multiplication problems up here on the board for you. Put a couple of multiplication problems up here. Let's go through and look at how we multiply polynomials. Now, this is the reason, these types of problems are the reason that I don't like you guys to use FOIL when you're explaining how we multiply binomials. Yes, technically you can think of multiplying your first, your outer, your inner, and last. Well, let's just look at a quick binomial. If I did x plus 2 times x minus 3, and I was going to multiply those together. You guys like to tell me that you multiply this by putting together the first terms. X and x is x squared. Putting together the outside terms. X and negative 3 is negative 3x. Putting together the inside terms. So we've put together our f, our o, our I, and then our L, our last terms. And then you combine your like terms, and you have your product of those two binomials. Well, when you get a scenario like this, where you don't have first, outer, inner, last, you have firsts, you have outers, you have sort of inners and more inners and some more inners and some more lasts, and there's just, this FOIL thing doesn't seem to hold up for that. But look at what you're doing when you're doing FOIL. You're taking x and multiplying it by x and negative 3. You're taking 2 and multiplying it by 2, actually by x and negative 3. You're just using the distributive property. That's all FOIL is the distributive property. Apply every term of one polynomial to every term of the other polynomial. And that's how we multiply all polynomials. That's why I don't like you guys to talk about FOIL, because FOIL just limits you to be able to multiply binomial by binomial. But if you think of all multiplication as distributive property, anytime there's a plus or a minus, anytime you're multiplying terms together or multiplying by terms, you want to think of it as distributive property because that covers every type of scenario. So that's what we're going to do here. We're going to distribute these. The direction I distribute doesn't matter because polynomial multiplication is commutative, just like numeric multiplication is. So we go through and distribute 2x squared times x squared plus 2x squared times negative 4. And here's what I'm going to do. I'm actually going to multiply these out. I'm not going to write those. Y'all know those. So 2x squared times x squared is 2x to the 4th. 2x squared times negative 4 is negative 8x squared. And I'm going to write it like this so y'all can see the technique I use to be able to combine my like terms. Now we'll move to the 3x. So 3x times x squared is 3x cubed. Well, I didn't have a 3x cubed here, so I'm just going to leave it in that open space. I had a 4th, didn't have a cube, so I left the open space, had an x squared. 3x to the 4th times negative 4 is negative 12x. So I try to line up my like terms as I go. Negative 1 times x squared is negative x squared. Negative 1 times negative 4 is positive 4. So I'll use this technique of distribute one term times the other polynomial. That's one row. The next term times the polynomial. That's the next row. The next term. And then just line up my like terms as I go. So that way when I go to combine my like terms, 2x to the 4th, I'm not hunting all over the place to say, did I get all my x fourths together, all my x cubes together? I just line up my x fourth column, my x cubed column, my x squared column, my linear column, and my constant column. So we should get 2x to the 4th plus 3x cubed minus 9x squared minus 12x plus 4. Okay. Assuming my arithmetic is correct, that should be correct. And then see, we're already in standard form and we're not having to rearrange and all of those good things. Now we just need to classify the expression. So degree first. The degree, the largest exponent is a 4, so we call it a quartic. And then the number of terms, 1, 2, 3, 4, 5. We don't have a special name for 5 terms, so we just call it a quartic polynomial of 5 terms. And yes, this is a 5 and not an S. Quartic polynomial of 5 terms. That's the product and its classification. I want you guys to pause this lecture here for a second, take a couple of moments, and try to find out what x plus 3 to the 3rd power happens to be, and then get that classified. Now we'll wait right here, guys. So hopefully you were able to get the simplified expression for this. Let's see what we come up with. X plus 3 quantity cubed. Really, really, really important that you understand you cannot distribute that exponent right here. Exponents are shorthand for multiplication. Multiplication is shorthand for addition. I can distribute a factor. That's a multiplication problem. I can distribute a factor across addition because multiplication, addition, shorthand. I can distribute an exponent across multiplication or division, because division is just multiplying by reciprocal. Because exponents are shorthand for multiplication. But since exponents and addition are not directly linked together, I can't distribute exponents across an addition problem. So I can't just treat this as x cubed plus 3 cubed. It doesn't work that way. Because if I did, I would get x cubed plus 27. When we go through and look, we can see x cubed plus 27 is not the product here. Here's what's actually going on. What does an exponent mean? What does an exponent tell me? It tells me how many times do I multiply this base by itself. So it tells me to take x plus 3, multiply by itself 3 times. So we're going to go through and distribute all this out. Now, just like if I'm multiplying any other number, 2 times 3 times 5, I don't do 2 times 3 and 2 times 5. I do 2 times 3 to get 6, and then I put that together with the 5. So I multiply 2 numbers at a time. Same with addition. Any kind of arithmetic we do, we can only combine 2 things at a time. So I'm doing the same thing here. I'm going to combine these first 2 together. I could have combined the last 2 together even if they were different. It's not going to matter because we know multiplication of polynomials is commutative, just like multiplication of numbers. So we go through and we're going to multiply. X and x is x squared plus 3x plus 3x plus 9. So x squared plus 6x plus 9 is the product of those first 2 polynomials. The next polynomial, x plus 3, we're now going to distribute it. The direction we distribute doesn't matter. Like on the last example, when I went left to right, I can come back and go right to left. Let's look at it. Let's go x to x squared is x cubed. X to 6x is 6x squared. X to 9 is 9x. And then we go with the 3. 3 to x squared is 3x squared. 3 to 6 is 18x. 3 to 9 is 27. So when I combine my like terms, I get x cubed from the first column, 9x squared from the second column, 27x from the third column, and 27 from my last column. So this is the product of x plus 3 to the third power. When I did x cubed plus 27, I lost these 2 middle terms, that quadratic term and that linear term. So that just kind of confirms for me that I cannot distribute exponents across addition or subtraction. Very, very important concept to know and understand. You cannot distribute exponents across addition or subtraction because they're not directly linked together by their definition. So it's just a bridge too far for you to be able to cross, for you to be able to use them together. All right, so this is the product there, and now we just need to classify it. Classify it, number of terms, by degree first. Degree is a 3, so it's cubic. And then there are 4 terms, so it's a cubic polynomial of 4 terms. We also call this right here, that's a binomial. X plus 3 to the third power is a binomial. We also sometimes call this process binomial expansion. Call that process binomial expansion. And there are a couple of techniques to actually speed this process of binomial expansion up without writing it out. Say I had x, to the third power. X plus 3 to the third power is not difficult to do. It takes about 15 seconds to work through it. But if I had to the 4th power, 5th power, 50th power, it doesn't matter what it might be. It gets very, very hard, not hard, very bunglesome. You're putting a lot of numbers in there. There's a lot of room for error. One miscalculation early on throws everything off afterwards. So we have a couple of techniques that we look at for binomial expansions to kind of clean it up and speed it up. And we'll look at one of them in class coming up very soon. And then another one we'll look at in the second semester to be able to expand binomials. But this technique is always your kind of default method, your default technique, and always remember, do not distribute exponents across addition or subtraction. Okay, that is it for just combining polynomials together. Next, we're going to take a look at how to look at a polynomial and be able to get a quick graph of identifying x-intercepts, y-intercepts, and just the general shape and direction of the polynomial. So give me a couple minutes and I'll get all that information up here on the board for you.